So, all right. So you said that it wasn't so bad, but guess what? It gets better. Your calculator has built into it the binomial formula. Okay? So it is called Binom PDF. Binom PDF. I'm going to show you where it is in just a second. And it has syntax. I guess I'll put it down here. Binom PDF. The syntax is NPX. Okay? We're going to tell it what N is, followed by a comma. We tell it what P is, followed by a comma, and then X. Okay, you know about this already? Yes, it's exciting. Okay, Binom PDF. So we don't have to remember the formula. We just need to remember when to use it. Okay, I'm going to point out here something else that may help us a little bit later. There's also a Binom CDF. Make that a C. CDF. Okay, Binom CDF. Also has the same syntax. The difference between the two, PDF calculates the probability. PDF calculates the probability of just X. Okay? CDF is the C stands for cumulative. So instead of just looking at the probability of X, it adds up the probabilities for X equals 0 up to whatever number we specify for X. So, for instance, this has more to do with the calculator than really the theorem. But I'm going to go ahead and try to settle this now. Okay? If I say Binom PDF 3, it's just 3. If I did Binom CDF, let's say like we're going to do now, whatever P was, 0.75 and 3, it calculates for me the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. So that I don't have to do that these 4 times in the PDF function and add them up myself. It does that for me. Does that make any sense at all? Little bit? Okay. All right. So just make sure you're paying attention to whether or not you're doing CDF or PDF. PDF is individual, just one value. CDF adds them up for us. Okay, and we'll have an opportunity to use both of those. I already gave you my little spiel about the rationale for the binomial formula. That's what I was doing with the boys and girls. So we already talked about that. All right, so let's see what's next. Just to make sure, let's back up a little bit, that we got the same answer. Let's try it out, because I still hadn't shown you how to do it. Okay, we're interested in the probability of exactly 3 successes. So I would binom PDF. Okay, N we already said was 5. P is 0.75 and X is 3. Okay, so on the calculator, I'm going to go to a new area, but we're going to be going here a lot. On the vars key on top, it says DISTR for distributions. We're talking about probability distributions. So I'm going to hit second and the vars key. Okay, and I believe it may, depending on which calculator you have, it may change a little bit. Choice A is Binom PDF. So you can either arrow there or you can hit alpha A to get there. But Binom PDF. Okay, and then I put in 5, comma, the comma is above the 7, 0.75, comma, 3. Let's see. I didn't get the what? Oh, okay, I see. Gotcha. Alrighty. All right. Thank you. Okay, so we get 0.237, which is exactly what we got when we use the formula by hand. Okay, so you don't have remember the formula. We just know when to use it. All right. Okay. So let's come on down here then. Okay. Oh, remember the probability of getting a green pie is 0.75. From earlier, yeah.
It's not. It's not.
Right. It might not be listed there, but it's this problem that, right, we talked about it earlier in another problem. So this is kind of following along. Okay. All right. Okay, we're ready to rock and roll now. Okay. So, example, finding probabilities when guessing answers. A psychology test consists of multiple choice questions, each having 4 possible answers, A, B, C, D, one of which is correct. Okay. Assume that you guess the answers to 6 such questions. Use the multiplication rule to find the probability that the first 2 guesses are wrong and the last 4 guesses are correct. That is, find the probability of wrong, wrong, correct, 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 correct. Okay? All right. Okay. I hope it wasn't that bad. All right. All right. So right now we're looking at one particular outcome. Okay? Not just any outcome that has 2 wrong and 4 correct. Okay? But we want to know about this. Okay? We've got 4 possible choices. We're guessing. So what's the probability of getting it wrong? If we're randomly guessing. What? 0.75? Okay? All right? Because 3 of them are wrong, 1 is right. Right? So it would be 0.75 times what? That's for the first question. Probability the next one is wrong is what? 0.75. So I'm going to square that. Probability of getting one right would be what? 0.25. And then there were 4 of them like that. Okay, so 0.75 squared times 0.25 to the 4th. That comes out to be. All right. I was feeling really good when I typed these notes. We're not going to do all of this. Beginning with wrong, wrong, correct, 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 correct. Make a complete list of the different possible arrangements of 2 wrong answers and 4 correct answers. Then find the probability of getting exactly 4 correct answers when 6 guesses are made. So they're just trying to make the point that I did earlier, that there are lots of different ways to get 2 wrong and 4 right. Okay, I'll write a few of them. I don't know if I'm gonna take time to write them all, but let's say we had right, or rather that's wrong, correct, wrong, correct, correct, correct. Okay, wrong, correct, correct, wrong. I mean, we could be here forever. All right, and that's just with this one staying in the first position. If I move him, then we're not going to write all those out. Okay, there are a lot of different ones. We'll just say that. Okay, but what we do want to do is find the probability of getting exactly 4 correct answers when 6 guesses are made. That's what I'll ask you on the test. And so you need to stop and ask yourself, could this possibly be binomial? Okay. Can it? Does it meet the requirements of a binomial experiment? Okay. Do we have a fixed number of trials? Yes. It's what? 6 questions. Okay. Probability. Do we have 2 outcomes? Yes. Right or wrong. Okay. Probability of success. Is it the same from trial to trial? Yes. Since we're guessing and each question has the same number of choices, it is the same from trial to trial. And again, because we're guessing, the choices are what? What, independent, right? Because we're guessing. Because what happens on the first one has no outcome on what we select for the next one if we're guessing. It's like tossing a coin. So it meets all of the requirements of the binomial experiment. So n in this case is what? 6. X is going to be What is a success in this case? Well, success would be correct, because that's what we're interested in. Exactly 4 correct answers. So x equals 4. Okay. P is, well, what's the probability of getting it correct? 2/5. Okay. 1 of the 4 is going to be right. And that's really, as far as the calculator, that's all we need. So we're going to do binom PDF 6.25 4. Has to be in that order. NPX. Okay. So again, I went to second vars. I'm going to hit alpha A now that I know that's where it is. And N is 6. P is 0.25. X is 4. And so we get 0.03. We'll say 0.033 for our answer. Was there? Yes, well, again, you know, most of this will be multiple choice. So you'll just pick from the choices. Okay. Some of the operating systems change. So your trials, you're going to put 6. You're going to put 0.25. And then for the X value, you'll put, was it 4? And then you have to hit highlight, paste, and hit enter. And enter again.
Okay.
Mm-hmm. Okay. All right. Questions about that?
I have a question.
Mm-hmm.
Now, with the binomials, then it must meet all requirements.
That's right. Mm-hmm. That's right. Mm-hmm. That is right. And like I said, there are lots of different ones. Even in this section or this chapter, I think the author talks about the Poisson distribution. We're not going to talk about that either. I used to try to get the second part of this class, but I wouldn't get enough people to sign up, so I gave up. Well, we could have talked about some of those fun things. Okay, next one. All right, there's a 1% delinquency rate for consumers with FICO credit rating scores above 800. If the Jefferson Valley Bank provides large loans to 12 people with FICO scores above 800, what is the probability that at least one of them becomes delinquent? Based on that probability, should the bank plan on dealing with the delinquency? Okay, so first of all, we see this problem, and again, we're starting to build our little tool bank. We'll ask ourselves, if we don't have any other clues, is this thing binomial? Okay, and so is it binomial? Okay. Okay. All right. At least. Okay.
So that means that 12 people and one doesn't.
So we have a fixed number of trials, right? Okay, we got the 12. Do we have 2 outcomes? Okay. Yep, delinquent or not. Okay. Well, I think I don't think the 800 has so much to do with it. It's just after, that's the particular group of people that they're looking at. That would be, I'm thinking, a good score. And so of those people, they said only 1% will have delinquency. So it's going to be delinquent or not. Okay, those are the 2 outcomes. All right, so we got fixed number of trials. We got 2 outcomes. Probability of success is the same from trial to trial. And the trial should be independent. Okay? Yes.
Is that a large enough sample size?
For which part?
It's just you're just numbers.
Well, the question was where the percentage came from. Now, when we started talking about the percentage of female governors, the only thing we had to base that on was the 50 people, the 50 governors. Versus here, the question would be, where did that 1% come from? And that's, on a very large number of people. Okay, so this is indeed binomial. Okay, what's a little tricky with this one is the fact that they ask us about the probability at least one of them becomes delinquent. Okay, this kind of goes back to what we talked about in chapter 4. I know y'all don't want to talk about that. But a couple of ways you could do that. Okay, you could add them all up if you wanted to. Probability of at least one would include 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 12. Do we want to do that? No. It'd be easier for us to say probability of at least one equals at least 1 minus the probability of 0 delinquent. Okay, but it's, we're talking about 0 delinquencies. We don't have to keep switching the numbers. We already said this thing is binomial, so we just want to know about the 0. Okay, so we do 1 minus, in this case I'm saying I want to let x equal 0 delinquencies. Okay, so I'm going to say binom PDF in this case is 12, p is 0.01, and x is 0. Okay, everybody okay about why we did it that way?
Why couldn't we use that other one where we added them all up?
Well, because we could, and I'll go back and do it that way as well. But remember that cumulative formula goes from 0 up to the number that we specify. Well, in this case, it's just really not enough of a difference for us to do it. The only thing we'd want to go up to would be 0. And then we'd end up subtracting that from 1, which is exactly what we're doing here. Okay? We'll see an example where we certainly will use that. Okay? So, binom PDF, you probably did it on your calculator already. What'd you get?
1.
Okay, 1. Okay. Alpha A. We got 12, comma, 0.01, comma, 0. Okay, I got 0.1136. Is that what you said? Okay, that's our answer. So, still, there's an 11% probability that they will have to deal with a delinquency. All right? So, based on that, should the bank plan on dealing with a delinquency? We'd say yes, okay? At least one is not a rare event. All right? Remember, and I'll emphasize this again when we go back to section 2, but remember, anything less than 0.05 we consider to be unusual. Okay, so 0.1136, that's not unusual, so they can plan on doing at least one. Okay, all right, let's look at another example. The textbook author purchased a slot machine configured so that there is a 1 in 2,000 probability of winning the jackpot on any individual trial, that should say. Although no one would seriously consider tricking the author, suppose that a guest claims that she played the slot machine 5 times and hit the jackpot twice. Okay, let's talk about these. Find the probability of exactly 2 jackpots in 5 trials. Okay, let's do that first. All right, before we get excited, we have to ask ourselves, is this binomial? Okay, all right, do we have fixed number of trials? Yes. Are the trials independent? We would think yes, if the machine is well made, yes. Probability of success, it seems, is configured so that it's the same from trial to trial, and the trials are independent. Okay, all right, so for part A, I'm going to do this over here. Okay, we're doing exactly 2 jackpots. We can say probability of 2 or probability that x equals 2. Okay, and so we're going to look at binom, what? PDF. N is what? 5. Okay, the probability of hitting the jackpot is 1 in 2,000, 1 over 2,000, and she says that she did it 2 times. Okay, so if we do that on our calculator, okay, all right. Okay, yes, we get our answer in scientific notation. If we wanted to write that out, 2496, we're going to say 0.000002496. Yeah, that's the probability of hitting the jackpot exactly 2 times. Okay, so not likely, but not impossible. Okay, all right. Then for B, it says find the probability of at least 2 jackpots in 5 trials. Okay, probability at least 2. That's a little different from at least 1, right? If we were to think about it, we could say 1 minus what? The probability of well, not at least 1. 0 plus what? 1. Okay? At least 2. We're using the complement rule. What's left out of at least 2? 0 and 1, right? At least 2 includes 2, 3, 4, and 5. So 0 and 1 are left out. Yes? Okay. How could I use my calculator to help me with this? The calculator will do both of these and add them up for me at the same time. So this might be where I would use binom CDF. Okay, N in this case is still 5. P is still 1 over 2,000. But X, I'm going to do 1. Okay, it says I want you to calculate the binomial probabilities for 0 up to 1 and add that together. Okay, I'm going to highlight this. This piece right here is calculated in this because we use this C. Okay, and so on my calculator, I've got 1 minus second distribution. This time I'm going to do alpha B to get binom CDF. Okay, we get 5, comma, 1 divided by 2,000, comma, 1. Okay, again, what binom CDF does is it adds up the probabilities from 0 up to the x that I specified, which in this case is 1. Okay?
Where does the 1 come from?
Okay, we said at least 2, right? And so what's not included in at least 2? 0 and 1, right? And so I want to subtract off 0 and 1. So what I'm having the calculator do for me is add up the probability of 0 plus the probability of 1. And that's what binom CDF does. If the problem had said, what's the probability of getting no more than 1 jackpot? then I would have just used binomial CDF, okay, with the 1. If it had said no more than 2, no more than 2, then I would have put a 2 there because it would add up 0, 1, and 2. Okay? We're going to talk about it even some more. Okay? And so anyway, we hit enter, and it looks like not a lot different. 24975. Okay. Okay, what was the last one? Should it be a 6? Okay. All right. Or okay. 1, 2, 3, 2, 4. Not much difference at all. Okay. So, does the guest claim of hitting 2 jackpots in 5 trials seem valid? What would you say? No, doesn't really seem valid. Okay. Interesting. Okay, questions on this? All right, very good. We subtracted that from 1 already? Yes, okay. And I did CDF. Okay, all right. All right, let's try maybe one more. Actually, before we try one more, let's see how many more do we have. Got a good many more. No, that's almost the end. Okay. Let's talk a little bit more about that calculator thing. Let's say we were interested in the probability. Let's see, which example do we want to talk about? Children, peas. Not the peas, okay. Okay. No M&Ms, okay. Children, okay. Children. Okay. All right, so we had a family of 3 children. Let's say 5, just to make it a little bigger. All right, what's the probability then of getting no more than 3 girls? Okay, so we got to pay attention to these little things. At least, no more than. Okay, if I'm talking about no more than 3 girls, I would calculate the probability of what? 0 plus the probability of 1 plus the probability of 2. Is 3 included here? Yes. Okay. Well, instead of doing that over and over and over again for those 4 different values, my calculator can handle this in one step. It would be binomial CDF. If we're doing 5 children, N is 5, P is still 1/2, X is 3. Okay, but that's CDF. It adds all of those up for me. Okay? All right. If I said the probability of at least 4 girls. Okay? Well, what's not included in at least 4? 0, what else? 1, 2, or 3. So that's why we could say 1 minus binomial CDF 5, 1/2, 3. Does that kind of make sense? Because binomial CDF goes from 0 to the X that we specify. So again, this is the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. And this is what I don't want. That's what's not included in at least 4. And so we say 1 minus all of that. Okay, what you have to remember about that cumulative function is that it goes from 0 to the x that we specify. Okay? All right. Let's see. What if we said... I don't know. What else could we say? No more than 3 girls. What if I say... I don't know. Well, if we said all 5, that would just be what? Probability of 5 girls would be what? What would we use? We just use PDF. Okay, we'd say binom PDF 5, 1/2, 5. Okay, so it just depends kind of on what the problem is asking us for. Okay, sometimes we might subtract that cumulative thing from 1, or sometimes we actually want the cumulative. Okay, if it said, oh, here's the good one, last one, probability of less than 3 girls. What would we do? It's what? Okay, that's 0, 1, 2. That's right. And so as far as using this feature of the calculator, what would we say? Okay, we could do cumulative binom CDF. Okay, n is 5, p is 1/2. What's x going to be? 2. X is 2. Okay, we just want 0, 1, or 2. We want less than 3 girls. Okay, all of that is really calculator speak. But you know, it's a helpful tool, but you have to understand how it works. Okay, all right, very good.